This is a video lesson continuing learning how to model regression equations for exponentials. We're going to do similar to what we did yesterday. We're just going to add a few more components before you start a project through the rest of the week. We're going to start with an exponential problem talking about the population in millions of the United States in the 1800s. And you can see our table here, 1800 to 1860. And you can see the population growth, 5 million, exploding, up 31 million, keeps growing, really grew a lot in those 60 years. And so what we would have is a exponential function. We're going to take a look at the scatter plot and run this. Now we're going to run this the same way we ran it yesterday. So you go into calculate, and you're going to go regression F3, and we're looking for EXP exponential, and just follow the same steps we did yesterday. When you run it for that data set, we get an A value of 5.337 and a B value of 1.03. So we're going to do A times B to the X power. That is my exponential regression equation. First thing we're going to do with this, like we did yesterday, we predict the population for 1870. Now when I put this in, I truncated my values. This was 0, 10, 20, 30, 40, 50, 60. And the reason I truncated them, because if you don't, that A value ends up something times 10 to the negative 23, a really weird scientific notation number. So to avoid that, I truncated. And so this would be 60, 50. So if I'm doing 1870, that means I'm going to plug 70 in for X. And I'll just plug this right in. You can use run matrix, or you can copy it into the table like we did yesterday. When I run this calculation to the 70th power, I get 41.83 million. So in 1870, that's what I would predict the population of the United States to be. Now, interesting thing, would this model be accurate today? I actually ran it for today, 220 years after 1800, and it gave us I think it gave me 4 billion or something like that, which is nowhere near accurate. So this model only fits for the 1800s. We're going to add a new element today. In C, it says, in what year does our equation predict the population would be 15 million? So when is it going to reach 15 million? And I can estimate where that's going to fall, somewhere in here, but specifically what year. And this is going to be fairly accurate because we're inside of this range of values. But the key is that I'm asking for the population to be 15 million. Well, that would be the Y value. So we're going to plug 15 in for Y, and we're going to solve this equation. And the directions on the practice problem will say, show your work. So I need you to show your work while you're solving these. So we plug 15 in for Y. First thing I'm going to do to solve is I need to get rid of this, following reverse order of operations. Nothing to add and subtract, but I can divide both sides by 5.337. So 15 divided by 5.337, when I divide that over, gives me 2.81. And what I have is an exponential in base 1.03. So how do I solve an exponential? We use the inverse. We take the log of both sides. This goes back to what you were doing the last 2 weeks. So to get rid of an exponential in base 1.03, I'm going to take log base 1.03. And I'm going to do that to both sides. So this log cancels out the exponential in the same base. So those two would cancel, leaving just x. And on this side, I have log of base 1.03 of 2.81. Now some of you had some questions last week about how to do that. The calculator will do that for you if you remember where the base is. Or you can use the change of base formula, which would be log of, in parentheses, we're going to go 2.81, close parentheses, divided by the log of the base, which again, so I'm doing the log of this number divided by the log of the base number. So the log of 2.81 divided by the log of 1.03. And I get basically 35. We're going to round that to 34.95, or 35 years later, which is 1835, the year 1835. All right, for our next problem, we're going to take a look at a logarithmic problem. We're going to look at the number of decades since 1900. So we're calling the 1900s, 1900 to 1909, decade 1. And then we're going to call the 1910s decade 2, 3, 4, 5, 6, 7, 8, 9, 10, up through decade 12. And we're looking at the life expectancy in the United States over each of those decades. And if you can see, around 1900, life expectancy on average, expected to live 47 years on average, got up into the 50s. Medical advances were getting up into the 60s, 70s. We're in the upper 70s now. Much bigger life expectancy. When we take a look at this, if you look at the scatter plot, it's actually going to go something kind of like this. It almost looks linear, but we know that if we track it linearly, it's going to grow. So life expectancy is 150, which makes no sense. What happens is you'll see at the end it starts to tail off. So what's going on here is that it's coming up and it's starting to flatten, which is what a logarithm would do. It's following the asymptote here, and it's flattening as it goes this way. And if you want to draw that scatter plot in the calculator, you would see that same pattern. So we're going to do this as a logarithmic function. Again, we're going to do it the same way as yesterday. You're going to go calculate F2, regression F3, and go over to log, and we're going to get ln x equation, and this is what you should get, a and b. So here is your natural log equation from the calculator. First thing we're going to do is we're going to predict the life expectancy in the 15th decade. So we were predicting down here for 12. We're going to do it for the 15th decade. That's decade is x. So I'm going to plug 15 in for x into my equation, plug 15 in, and just run this through. Make sure you're following order of operations. Make sure you type it in the calculator right. The calculator will do the order for you correctly. But this plus all of this being multiplied is 80 years. And the reason why I bring up order of operations is if you add these together, then multiply by this, you're breaking order of operations. Order of operations says multiply first, so you have to multiply these, whatever ln 15 is, times 13.86. Then you add this in. So follow order of operations. Gives me 80 years. So I expect 15 decades later, which is another 3 decades from now, life expectancy will be around 80 years old. Do have one more problem where we're going to solve. And question 3 for this one, it says predict in what decade the life expectancy will reach 85. So if this pattern continues, when will life expectancy get all the way up to 85? So life expectancy is y. So I'm going to plug that in for y into my equation from the calculator. First step, and I'll zoom out a little bit here so that we can see the whole thing if you want to stop and write all this down. But the first step is I need to get rid of this 42.5, so I'm going to subtract this over. So I subtract 42.5 from both sides, and it gives me 42.5. Then, now that this is gone, I'm going to take this and divide by 13.86 on both sides. Gives me 3.066, and that equals the natural log of x. Now that this is gone. Now how do I get rid of ln x? Okay, this is a logarithm. So we need to, like we did the last 2 weeks, exponentiate. So we're going to exponentiate using base e, because this is the natural log, which is log base e. We're going to do exponential base e. This is one of our properties where we know these two cancel out and leaves x. So when I exponentiate in base e to the 3.066 power, I get 21.5. So 21.5 decades from 1900, and we're about 12 decades since then. So we're talking another 9.5 decades from now, quite a ways before we supposedly reach a life expectancy of 85 years. As we know, a lot can happen between now and then, but that would be the prediction.